All right, in 7.2, we're looking at the inverse secant, cosecant, and cotangent functions. Let's begin by identifying the domain and the range for all three of these. All right, we would determine these based off of making their original functions one-to-one using a domain restriction. Okay, so starting with the inverse cosecant function, its domain is going to be the range of the original cosecant function, which is nothing more than negative infinity to negative 1, as well as 1 to infinity. Okay, so I'm only able to plug in numbers into this function that are smaller than negative 1 or larger than positive 1. All right, now the range is accepted to be negative pi over 2 to positive pi over 2. So that's from restricting the domain of the original cosecant function in order to make it one-to-one. All right, but we have to exclude 0 from that, meaning 0 degrees or 0 radians, and that's because the original cosecant function is undefined there. You have an asymptote in terms of its graph. Okay, what quadrants are we talking about this yielding? From negative pi over 2 to positive pi over 2 is 1 or 4. Okay, so think about this in terms of positive and negative quadrants. So cosecant's positive in quadrant 1. Okay, it's also positive in quadrant 2. It's negative in quadrants 3 and 4. So this range restriction says we're eliminating angles in quadrants 2 and 3, thus keeping quadrant 1 where we're positive, and then quadrant 4 where we're negative. Okay. The inverse secant function, it has a domain from negative infinity to negative 1, as well as from 1 to infinity, just like inverse cosecant did. Now its range is going to be from 0 to pi, where we can exclude pi over 2 or 90 degrees, right? So think about the reasoning behind this restriction. So inverse secant, secant is positive in quadrant 1. It's negative in quadrant 2. It's negative here and positive here. So by this range from 0 to pi, we're ruling out quadrants 3 and 4, allowing us to keep one positive quadrant and one negative quadrant. Okay, so we're in 1 and 2 here. All right. And the last function, inverse cotangent, it has a domain of all real numbers. You can plug any number in for x, and then the output is going to be from 0 to pi. But notice I'm excluding 0 and pi. That's because the original cotangent function is undefined at those two values. Okay, so that's yielding quadrant 1 and quadrant 2 angles. And the reasoning on that would be pretty similar to how we restricted the range for the inverse secant function as well. All right, so let's get to some examples here. Find inverse cotangent of negative radical 3 without a calculator. So let's think of that as being over 1, to where the negative radical 3 is an x value, the 1 is a y value. All right. Now we just got done saying that inverse cotangent can yield angles in quadrants 1 or 2. Well, I can yield out quadrant 1 angles because of the fact that we're evaluating with a negative number here. Okay, so that means the output for theta, it has to be in quadrant 2. Okay, so let's draw this out. Okay, so here's the angle that I'm after, all right, and it's going to be based off of x being negative radical 3, y being 1, r is of course 2 here, so that's a 30-degree reference angle, making theta 150 degrees. Okay, so I'm going to say inverse cotangent of negative radical 3 is 150, or if we were asked for radians, that's of course 5 pi over 6. Okay. All right, next example is a very important example. All right. It's important to understand that the reciprocal identities do not apply to inverse trig functions, okay? So what I mean by that is if you're working with the inverse cosecant function, you cannot say that it's equivalent to 1 over inverse sine of x, all right? And the reason I bring this up is because we have to know how to evaluate inverse cosecant, inverse secant, and inverse tangent on our calculators, okay? The original trig functions of cosecant, cotangent, and secant, we are able to evaluate those on the calculator using these reciprocal identities, right? But we're not going to be able to do that here, okay? So let's find inverse cotangent of -2 using a calculator. We'd have to use a calculator here because if we tried to approach it the same way as the last example, you wouldn't have a nice reference triangle to work with to where you could come up with an exact value for this angle by hand, okay? So we have no choice but to approximate it with the calculator. What you absolutely can't do is try to say that inverse cotangent of -2 is the same on the calculator as 1 over inverse tangent of -2. These are not equal to each other, okay? So here's going to be the approach. Reason out what quadrant this angle has to be within, okay? So think of this as over 1, that's an x, that's a y. Inverse cotangent can only yield angles in quadrant 1 or quadrant 2. It's got to be quadrant 2 here because that input is a negative value. All right, so let's draw this out. Okay, so this is the angle that we're after. X is -2, y is 1. You can quickly find r to be radical 5. Clearly not a special right triangle, hence the need for the calculator. All right, so if I can't use 1 over inverse tangent, then what's my approach? Well, you have to relate this back to one of the 3 inverse functions that the calculator is programmed for, okay? The calculator is programmed for inverse sine, inverse cosine, and inverse tangent. Out of those 3, the only one that you can use here is the inverse cosine function. That's because it yields quadrant 2 angles, just like inverse cotangent is supposed to. Inverse sine and inverse tangent, they don't yield quadrant 2 angles. They only yield quadrant 1 and quadrant 4. So we're going to have to use the inverse cosine function. To do that, it requires me, off of my picture drawn here, to reason out the ratio for cosine. Cosine is the x value of -2 over the r value of radical 5. So that means inverse cotangent of -2 should be the same as inverse cosine of -2 over radical 5. Okay, now if we were to type that into our calculator, notice I've already done it here, I end up with 153.435 degrees, which is, of course, in the second quadrant. Okay. All right, last example. Now, find cotangent of inverse cosine of 1/3 by hand, giving an exact answer, okay? So here's a composition of functions. Let's start on the inside first. Inverse cosine of 1/3 is going to yield an angle. The 1 here is an x. The 3 is an r. I can tell you this is going to yield a first quadrant angle since that is positive 1/3, okay? So let's draw this out. Here's theta, 1, 3, I'm sorry, 3's up here. And then that's going to make this 2 radical 2, okay, using Pythagorean theorem. All right, so notice I can't reason out theta, its exact value here, but I don't need to know its exact value. I'm just trying to find cotangent of this angle by using x over y from the triangle. Clearly want to rationalize here. That's going to take me to radical 2 over 4. And of course, I could check this on the calculator. All right, so we typed in radical 2 over 4. There's an approximation for it, 0.35. All right, and then type in cotangent, which would really be 1 over tangent. You can use the reciprocal identity here because that's the original cotangent function. So I'm doing 1 over tangent of the inverse cosine of 1/3. And see how I'm getting the exact same approximation as radical 2 over 4 yielded.